production runs, you know. All right. So now let's take a look here at fictional vibration. Frictional, not fiction. Whoops. Frictional vibration. Okay, so if you have a real high radial load on a bearing, you will get, even though the bearing might be in perfectly good condition, you can get a lot of noise out of it because you don't have any enough lubrication in it. Okay, so let's go look at the next one here. So here's an extreme example, and where you got a lot of force in this bearing, and you can see here the bearing is literally getting hot. Well, the reason it's getting hot is it's got a real high frictional load, because when you increase the load too much, the lubrication breaks down. Well, there's another really nice thing. It doesn't even have to be highly loaded. If the lubrication starts to break down, it starts to give us the same type of noise, and it's a metal on metal rolling noise, okay? And it occurs at very high frequency. It actually occurs at the resonant frequencies of the inner and outer race and the bearing housing, okay? So rubbing, sliding, or rolling with insufficient lubrication causes metal on metal friction noise, which is random and high frequency. So let's take a look at a little bit more. So here's just some examples of a complex structure where you got loads or lubrication problems, and it radiates out. This is a real example of a compressor, and you can see here the bearing got really, really hot. It melted some parts of the bearing. Obviously, they bought a system so they could monitor that and avoid that, because at the time this happened, they didn't have a system like that. And I think I have a picture here. Here's a close-up of a bearing where there's been a lot of rubbing and contact, a lot of friction because the surface broke down. Here's another rolling element bearing that you can see, and it was rubbing really hard on this side because you can see the tracks in it, and it got so hot that it actually started to break down the inner materials. And the whole goal is to catch things way before this happens. If you can catch that in the lubrication cycle, and it's not done any damage yet, and you can figure out why it isn't lubricating, and you can save the bearing and save a whole outage just by making sure the bearing's greased. Had a case on a paper machine where all of their high frequency friction vibration readings went up at once, all of them on a paper machine. And they called me up, oh, something's wrong with our vibration measurement. So I went over and looked at it. No, I said, there's nothing wrong with your equipment. And I said, but you do have something wrong with every one of the bearings. I said, what happened between now and the last time you took readings? And they didn't know, and they're dig into it a little bit. About a half hour later, they came back and said, we greased these bearings the day before we took readings. I said, what grease did you use? Well, I don't know. And they looked at it, and it was a XYZ brand that starts with a C, a big C. And they checked it, and they go, I don't know. And fortunately for them, there was a lab real close. And I said, well, let's have the grease tested. So they went and tested the grease, and the grease was a low temperature grease, and this was a high temperature application. And on the barrel, it said high temperature grease. And I said, well, there's no way. And so they sent this company that starts with a C the report, and they came back and said, you're right. It's not high temp grease. And it turned out that this company had taken an entire manufacturing lot of high temperature grease barrels and filled them with low temperature grease. So again, the good news was it only ran for about 16 hours with that grease in it, and the guy came around and took readings, and then I was there within 24 hours, and within about 35 hours we identified the problem. They shut down the machine, flushed the grease out of the bearings, put the right grease in, and got it back. And they didn't have any bearing failures, but of course they wound up getting, I think it was $60,000-$70,000 from this company and stuff to cover their potential liability in early bearing failure. So yeah, these are really cool things. And again, we tried to take the mystery out of this high frequency stuff with our bearing detection unit. Okay. Now, common attributes of frictional vibration. Again, expressed as in a high frequency range, even higher than the meshing frequencies. At TPI, we would consider that as high as about 300,000 cycles per minute to up to about 1.2 million cycles, or 5,000 hertz to 20 kilohertz. It'll start a little lower than that, but if you're taking acceleration, you'll see it. But the BDU is a filtered acceleration reading, so it really isolates these well. The vibration units are normally in acceleration G's of gravity, where 1 G equals 9.8 meters per, anyway, don't worry about that stuff. Or bearing detection units, a filtered acceleration measurement. And I would say I would rely heavier on that field bearing detection unit, because that will just help you with any lubrication related things. Friction typically does not relay through an entire machine. And the higher the frequency, the less distance it travels through metal, okay? Mm-hmm. So that earthquake I experienced the other day didn't have any high frequency components to it, you know? And if it did, I never would have seen them 50 miles away because it would have been soaked up, okay? So due to high frequency, frictional vibration has less direction but increases in amplitude when close to the source. So the closer you measure to the source, it will get dramatically higher. So what type of problems? Rolling element bearing lubrication. That's probably the #1 problem. Journal and fluid film bearing rubs, kind of yes, kind of no. And the reason I say that is, if it's a small journal bearing machine, yes. But if it's a really big one, like a power turbine or something like that at a power generation station, they're going to have proximity probes on it which measure displacement directly. So if they developed a problem, they're going to first see the actual shaft moving towards the babbitt material. So there's no rolling element bearings in those. So for a big machine, no, but for a small, I've seen a small dresser turbine that powered a paper machine, you know, and that didn't have any journal bearings on it. So we used just regular accelerometers and looked at acceleration. Pump cavitation causes the same high frequency range type stuff. So if you get a pump and it's cavitating, you can catch it early, and that'll be both present in acceleration, and a BDU will also pick that up. Gear lubrication, of course, electric motor bearings and rubs. So sometimes you'll get a rub in an electric motor, and you can see those rubs. Again, think of it as no lubrication. Lobe and screw compressors, when the friction goes up, whether it's wear or lubrication causing high wear, you just don't worry about where it's coming from, just worry it's gone up. So they're always high, but they'll go from high to even higher. And when they start trending up is the time where you need to start scheduling repair. So source identification strategy, meshing, passing, and frictional vibration. Let's look at this. High frequency machine faults do not travel far through metal and can be localized to an individual machine or even a component within the machine. Now, can you hear that noise? Should be able to hear that noise. Can you hear that or not?
What's it supposed to sound like?
It actually sounds just like a machine. Hang on a second. I think I have to do. Hang on a second. Where
if
did
anything, I hear our laptop fan a lot more.
Yeah, hang on a second. Let's go to. I think it's Mike. Yeah, I'm just checking some settings right now. Mike, I want to keep sharing. Speakers, microphone. Try this again. Mike. My computer just responds so slow. Spatial noise suppression. No noise suppression.
Okay, can hear now.
I hear.
Okay, you probably hear my 3D printer in the background.
Oh.
Oh yeah, that was mic frequency background.
Okay, I think. Hang on a second.
Machine
Spatial
phone.
audio, noise
Those with high
suppression.
frequency
Come on.
characteristics do not travel far through
High
metal,
fidelity.
since that coupling interfaces heavily attenuate
Okay.
the signal.
I think we're okay now. Let's go back to the presentation if I can figure out how to do that.
Okay,
Well,
we
now
can
I
hear.
can't even hear. So now I can't hear. You can't.
Oh, we can hear. We can hear.
Yeah, that's my. You're hearing that? Whoop, 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 whoop. That's my
Yes,
printer.
yes, yes.
Oh,
We
that's
can hear
also a
now.
printer.
Oh, your printer.
Yeah, hang on a second. Let's go back.
That is a triple axle 3D printer at XYZ radius.
Yeah, that's a Bamboo Labs 3D printer, and it's pretty cool.
Back then, during my university, I was in IET as well, the institution, the Engineers of Technology.
Yep.
We used to do workshops on developing 3D printers, but I was mostly focused on software demonstration only.
Yeah, now this tends to be the real popular, and I'm trying to bring back your other screen here, and I don't know why it's doing this. Microsoft, in my opinion, has not done a very good job lately. They're way too concerned about charging you every year for something, and much less concerned about giving you usable results.
Oh my
Okay,
God.
I can see, but so what would happen here is, let me just go back on this screen. You see, this is, I hate this because it's not showing me. You're sharing your screen. I want to do that. Why is it? Huh. It's not letting me. Is it? Look at the share control bar. I got that. I got this. Okay, got that. But it's not letting me show. Hang on a second.
Is that so?
Oh, that's the sound of the 3D printer.
Oh,
3D printer is moving in the back.
Yeah, okay. It's. Normally I have a presentation screen here and I can see what's coming because I think that's why the sound isn't working. But hear that sound?
No.
Okay. Oh, darn. Anyway, it will make it literally sounds like if you have like a stethoscope or if you use earphones with our devices, it sounds just like this. And then you go. Second, all the way up. It's probably noise canceling it out. Noise gets louder. Now, noise gets loud. Smart sound microphone. No, I don't want that. It's giving me all these things. No, I don't want noise suppression. No, I don't want spatial audio. Let's see.
Yeah, the
Sorry,
new
Mike.
resolution.
Sorry, Microsoft. I know I'm old, but I'm not that old.
oh, no worry, no worry.
The newest Microsoft Teams has messed up a lot of people.
Oh, yeah, it's really, really terrible. It's, okay, I think here's the bad parent.
No, sir, I think your mic is gone.
Oh, my mic is gone.
Oh, no, your mic is okay now.
Okay, I think it was sound canceling me out because it's pretty loud. Okay, so it's just simply the amplitude increases. All right, So key takeaways. Machine vibration can be grouped into 3 primary categories. Free body vibration. Not too many people teach this, but I think it's really logical. Meshing and passing vibration and frictional vibration. 3 basic things that a machine puts out. Body vibrations, they're measured in units of velocity because they're lower frequency oriented. Frequency range, they're very directional, so if a machine is shaking axially, it'll push that axial motion up and down the entire machine train. It's like if you have a tire that's out of balance in your car, you can feel it all over the car, you know. The people, it's not like if you have one in the front, the people in the back seat can't feel it. Nope, everybody's going to feel it because it's low frequency. Okay, and then we have free body vibration, and then we have meshing and passing vibration. So I'll send these to you so you have some time to review them.
I appreciate it.
And then finally we have this frictional vibration. Units of acceleration or
BDU.
Yeah, the video. Yeah.
BDU.
Yeah, BDU. And that's something unique to us. I talked to Jim and I said, we were talking back and forth on this years ago before he worked for TPI. And I said, you know, I find it funny that some companies will make up their own reading and then claim it's like miraculous. I said, all they're doing is filtering acceleration. That's all they're doing.
Yes.
You know. And so he goes, yeah. So he came up with this. And basically, we take acceleration multiplied times 10, and then we apply a high pass and low pass, a high pass filter to it to make sure that low frequency isn't involved. And then it comes through, and we just measure it. And it's very, very reliable and good at predicting lubrication type issues. Okay. So we kind of keep it simple, and so free body measurements, and we use ISO. They have a spec for that, and we also measure 1, 2, and 3 times RPM bands. All our devices do that. Mm-hmm. Okay. We also measure these things they call VA bands, where we automatically have 6 different frequency ranges we take. It not so much helpful for a beginner. But sometimes could be helpful for a more advanced vibration person. You can verify, like it sometimes could be hard to tell the difference between something that's loose and something that's out of balance. And they'll look, but if you see a lot of multiple frequency bands, that when you see 1, 2, 3 band, that's probably out of alignment. 1, 2, 3, 4, 5, 6. If you see the VA bands all going up, then it's more likely something that's loose. Okay. So the types of things you can measure with that: unbalance, misalignment, fluid film, journal problems, looseness, bent shaft, resonance, belt drive faults, and shiv misalignment. Now we come up to the meshing and passing vibration. What do we measure for that? We measure total G's of acceleration. We also have a thing called crest factor, which will show you like a ratio between low frequency and high frequency noise. So if you see a real high number, you know it's high frequency noise, so you know it's not any of this low frequency stuff. It's something up here or up in here. So we measure crest action. We also do a real fancy thing called demodulation or enveloping, and that can again help an expert pinpoint problems, but only the more advanced instruments do that. And then here are the type of things we can identify with those, that those help us identify. And then frictional vibration measurements, BDU or bearing detection unit, demodulation can help us with the bearing. You can use demodulation to say, oh, it's the inner race, or oh, it's the outer race, but again, I don't have much use for that normally, you know, and stuff. And then total G's of acceleration. Again, I don't worry about this as much because I'm doing the BDU, which is a little bit better. But what can we do? We can look at rolling element bearings, journal bearings, rubs, cavitation, gear lubrication, electric motor bearing, and rubs, and then lobe and screw compressors. So yeah, you can see there's some overlap in these readings, okay, especially these two, there's a little more overlap, but not much, and so these are really, really good. Okay, so I think that concludes that, and then, okay, now I'm going to introduce you to a real simple principle, and this is how rolling element bearings fail. And by understanding there's a frequency bias. High frequency things tend to give us much earlier indicators, but they're also high frequency. So some of the measurements have a bias towards high frequency, and acceleration is one of these. So we're going to kind of demonstrate this approach and show you how you can quite easily set up your system to identify bad bearings. So the very first thing to go up is BDU, and I'm just going to put in quotes acceleration, although BDU is a little bit better because of the filters we place in it. So bearing damage units. So the very first thing to go up is a bearing starts to fail are BDUs. The great news about this is if you can lubricate it and bring the vibration back down, or figure out if you're getting water in the bearing or something, you got a bad seal. If you can figure that out, you can extend the life of that bearing a long, long time if you fix it when you see this go up. Very high frequency, that rubbing noise that you would hear.
Video.
At that point in time, you have approximately 6% of the bearing lifetime left. So we use a formula to calculate bearing life. It has to do with load of the bearing and some other factors. And it's called the L10. And it's commonly used by companies like SKF. When you're doing an application, they'll figure out L10, and they'll say, oh, well, this bearing should last 150,000 hours or whatever. And they're very good at predicting that. Okay, so that you have approximately 6% of the L10 left. BDUs, and there's our bandwidth and mathematical amplitude correction. And then what we do is we look at it from 1 kilohertz to 10 kilohertz times 100. That's kind of the formula we use. Okay? So the tech guys will want to know that. It's sensitive to high frequency friction and lubrication condition. Early stage of bearing failure, bearing check for lubrication and damage. So I wouldn't tell somebody, oh, take your machine apart. I say, go get your grease gun. I grease it. Then I take another reading, and if it goes down, then go back, say 2 or 3 days later, and see if it came back up or stayed down. Mm-hmm. If it came back up, you're getting contamination. You got to do something. If it went back down, you need to grease it more often. Just you let it get too dry. Real simple, real practical. Acceleration will follow BDUs. It'll lag a little bit, but it's very, very similar. But now you have probably 3% of the L10 left in your bearing. Overall acceleration units, a lot of the same thing. High frequency bias, that's the high frequency stuff. Early bearing wear, impact of rolling elements will cause it to go off. Early stages of bearing damage may or may not be visible. One of the problems you have is when these type of units go up, the first thing the mechanics do is dig their fingers into the grease to feel if they can feel anything. Then they'll flush it out and look and see if they can see anything. And if they can't, they'll say, oh, you don't know what you're doing. We had a paper mill that got a microscope that was a 3D microscope. So it magnified, but it really let you see the different layers of like wear. So they would cut the bearing, and this guy was notorious for pulling bearings out when he just got a high BDU reading. But he would tell them, okay, we're going to cut the bearing and look at it. And you would look at that compared to a normal bearing that had worn in but wasn't giving high frequency units. and you would see all, but you couldn't even feel it with your fingernails, okay, when you rub the bearing, but you could see that there were actually pock marks in the bearing with their 3D microscope. So he made believers out of them. But the nice thing is, you're still not in too much danger if you don't take it out. You just have to tell people right up front, because it builds the trust. You won't always see bearing damage when you pull these out. You won't always see it. However, velocity then goes up. So now the bearing has peened out clearance within the bearing, and it's starting to move more than normal. The bearing is, the actual elements. Now velocity, which is lower frequency oriented, starts, everything else continues to be high, okay? Everything else continues to go up. But now, if you took it apart and you let velocity come up, this is the kind of thing where you're not going to extend the life unless you're greasing it constantly. You know, you're going to pull the bearing apart, and there's going to be some damage there. Okay, so you only have about 1%, 1.5% of the life of the bearing left. And then I'm going to explain something you see in this. Now we're going to look at, okay, velocity. It's vibration neutral. It doesn't bias high frequency and low frequency. It can't see high frequency real well, but there's no bias there. Clearances of the rolling element bearings are opening up. Bearing elements have visible damage. That would definitely, you pull it apart when velocity is up, you should see some damage somewhere. And that's the late stages of bearing damage. And now if you are really a desperado here and want to measure displacement, that goes up as the bearing is failing, you know. Now, you will notice that I put up here this BDU, and you'll notice that it turns down. Oh, can you see my red laser marker there?
Yes.
Yeah, okay. It turns down, or it can go right up through the roof as the bearing fails. Well, why would it ever turn down? And, I don't have a bearing handy. I probably do. But if you've ever pulled a bearing apart that's been really hot and been really damaged, many times as you pull it apart, you look and there would be a rough zone there, but it's covered with like a black, what appears to be plastic. It really technically kind of is. And what it is the grease bakes itself and turns basically into a solid. And now the rolling elements, let's see if we do this, like here's the outer race of the bearing, and here's the balls running through. Okay.
Is it like a residual grime, the leftover grime?
Yes, and the bearings start to float over it, you know?
Yes.
It is especially true if a bearing is not highly lubricated. I had another facility that had been using our system a long time. They called me up. I went over, they were over in the Bay Area, very good customer. I went over and, it doesn't work, it doesn't work. And why doesn't it work? Well, this pump here, we took readings last Friday, and it was everything was perfectly smooth. And then Monday, he said the bearings were on the floor, and it was still running. But we took another reading, and the reading was not high, it was almost zero. And I said, well, that's because the bearing, in fact, the way they said it, well, the bearing was nearly zero. And I said, well, look around on the floor and see if you can find balls for the ball bearings. And they did. They found them on the floor. I said, well, the reason it was so low is there was no bearing, and it wasn't rubbing. The coupling was holding it centered. And I said, so it was, in essence, an air bearing. There was no bearing there, And they go, and I said, and then look at your readings you took on Friday, because this was on a Monday. I said, these readings are 10 times higher than any of your other readings, and your alarm levels have been raised. So I took them back in the software and showed them historically, it kept going up, and somebody kept raising the alarm level. Okay, until it was ridiculously high, at 2 or 3, it was ridiculously high, and nobody, it's alarm. I mean, I don't want to take that apart this weekend. Let's just raise the level. That's what they kept doing, and it was high in velocity, and they didn't have any alarm levels set. you know. And so I said, no, look at all this. You don't have any alarms. Look at the trend. I said, all these trends are going up, and the one you just kept raising the alarm level. And I said, till finally, no more bearing. So these are very, very useful, very useful. So you have approximately no percent of the bearing life. You don't want to put your tent up and camp out. I had a facility, a mining company. I went out and I took a reading in. It was the highest reading I've ever seen on a running machine. And I took one reading, and instead of taking readings all over it, I said, good enough. I hopped in the truck and just go. You didn't take very many readings. I said, because it's going to blow up. And they didn't believe me, you know. So I showed them. They said, well, what's wrong with it? And I go, everything. And they go, well, what do you mean everything? And I said, look, it's been vibrating so bad for so long. The bearings are bad. It shows electrical problems. It shows mechanical problems, looseness, misalignment. Everything that's possibly wrong is all wrong, you know. And they didn't want to believe me. Oh, no, you know, don't, no. And I said, no, everything is bad. And I said, I would shut it down right now. I said, because it's not going to last. I said, it could blow up tonight or tomorrow. Overnight, it blew up. And they said it was a good thing no one was there, because this was like 700, 800 horsepower electric motor, big vertical thing, huge.
Yeah,
And
very
they said it was bent and pieces of it were all over the place. You know, the rotor came out of it, everything, total destruction.
Oh, how irresponsible of them.
So the very next day, that afternoon, is when they called me up and they said, you're not, so we don't believe this, but exactly what you said would happen, happened. And they said, we want to place an order for 2 of your systems. So yeah, it's quite interesting. So there's a big low frequency bias to displacement readings. I have another course that explains why. And so clearances of the bearing continue to open up and create looseness. So you look at a bad bearing and it also looks like looseness. It looks like misalignment. Everything about it looks bad. But and if you catch it early enough, you should have been able to see it coming, so you should know it's the bearing. Okay. And key takeaways. Okay, selecting the proper vibration unit can be the key to identifying the early stage of rolling element bearing failures. Low lubrication, which you can enable a correction and fix things. Early bearing fault detection. Just too late bearing fault detection. In other words, if you don't pay attention to anything, it can be just too late, you know.
Yeah, true.
That's a takeoff of the American about 20 years ago. All of the Silicon Valley and all the car manufacturers, they called it just-in-time inventory delivery, you know. And that means if I'm making cars and some other plant makes the tires, I get them. I don't have to have a big inventory because I always have a steady flow, just-in-time inventory. And so I coined their phrase and said, just too late bearing fault detection. Okay. So you don't want to have that. Okay. And stuff. So that concludes kind of the fundamental stuff on it. And I think, yeah, it's back to the beginning. So yeah, and then you'll see here. Should still see it. That's my grandson. They
Wow.
up to